Okay, let's get started. Good morning, good afternoon, good evening. Thank you very much for joining today's tinyML talk. I am Wei Xiao from ARM. I will be your moderator for today's session. Huge thanks goes to our tinyML talk sponsors, DeepLight, Kixel, Edge Impulse, Reality AI, Maximum Integrated, and SyncSense. We have additional sponsorship slots available. If you're interested in make this program possible, please email betty@tinyml.org. Let's watch a short video from our sponsor, Kixel.
Kixo AutoML is an intuitive end-to-end machine learning platform that automates labor-intensive tasks. Data from user-selected sensors can be collected and labeled in real time or uploaded from an existing data store. Features are automatically extracted from the data and weighted based on importance. Kixo AutoML offers a wide variety of machine learning algorithms, including regressors, decision trees, and neural networks. A selected model is deployed for live testing with one simple click.
Let's take a look of our next tinyML talk agenda. On Tuesday, September 1st at 8 a.m. Pacific time, we will have a presenter, Suri Chirasaria from Arizona State University to talk about how adaptive video subsampling can be applied to energy-efficient object tracking. Christopher Carlson from BrainChip will introduce the Akida neural processor. If you want to present in our series, please email your proposal to talks@tinyml.org. So our second speaker today is Urmish Thakker from ARM Machine Learning Research Group. Urmish's topic today is pushing the limits of RNN compression using Kronecker products. Urmish is a senior research engineer working at ARM's Machine Learning Research Lab. His focus is efficient execution of neural networks on ARM devices. A couple of his work has led to multiple patents and publications. Prior to ARM, Urmish also worked with AMD, Texas Instruments, and Broadcom. Urmish, the virtual podium is yours.
Thanks, Wei, for that introduction, and good morning and good evening and good afternoon to everyone on the call today. I'm very excited to share some of the preview of research around efficient execution of neural networks that we have been doing within ARM's ML research group. Hopefully, by the end of this presentation, you would have taken away a few key things. One thing is that if we are able to push the limits of compression, then we will be able to really enable a large range of applications on a kilobyte budget. And when I say push the limits of compression, I'm talking about 15, 30, or even 40x compression. Now, traditional compression technologies like tuning and low-rank matrix factorization do not allow us to get there. And the two new techniques that we are exploring within ARM's ML research group, Kronecker Product and Dope Kronecker Product, might allow us to get to where we want. So before I start off, I wanted to introduce the ARM's ML research group, specifically the team that I work for. So the aim of my group is to develop new compression technology for ML on kilobyte budget. So we are exploring new techniques or tools for compression that can support large compression factor. My work specifically targets LSTM networks that you probably see mostly used for time series data or natural language processing applications. Now, these LSTM networks have generally large dense layers, which require significant compression. So to set up the motivation, let's see what you can do if you have a tool that allows you to compress an application by a large factor. So what you see on the screen here are three popular applications that either are currently running on edge device or we want to run them on an edge device. These are KWS or keyword spotting, HAR or human activity recognition, and a chat application. So the KWS application at around 240 kilobytes, when compressed by around 16x, that gives you around 15 kilobytes. This is assuming 32-bit precision. So after say an 8-bit quantization, you're talking about 4 kilobytes. So earlier, this application might be running on a higher Cortex-M device, but now with 4 kilobytes, you might be able to run it on a say Cortex-M0 device or even hard code BB8 values in your accelerator. For the HAR application, after 20x compression, you go from 1.5 MB to 75 kilobytes. And if you do quantization, maybe around 20 kilobytes. And again, earlier you might not be able to run it on a Cortex-M device, but now you might be able to do it because of a large compression factor. The chat application is, impossible to run on a Cortex-M device right now with 25 MB space that it requires. But after 25x compression and probably an 8-bit quantization, you're looking at around 250 kilobytes. And again, you enable this application to run in a Cortex-M device. So what happens is that when your device gets smaller and smaller, you are able to run these applications in an always-on scenario and sort of prolong the battery life of the device that is running this application. And you can probably get your application to run on a cheaper device also if you have this capability. So what happens when you use traditional compression technologies to compress these applications? And with traditional, I'm talking about pruning and variants of pruning like magnitude pruning or L1 pruning, and low rank matrix factorization and variants of LMF like SVD. So if you take the HR application and compress it by 20x, none of these traditional compression technologies allow us to get there. We lose almost 3 to 7% of the accuracy. With keyword spotting, the story is similar. You're now using around 3 to 4% accuracy. And for language modeling, so language modeling is the chatbot application or the workhorse of a chatbot application. And in case of the language modeling, the accuracy metric is generally perplexity. And for perplexity, the lower value is better. So for the language modeling application, if you compress by 25x, using pruning, your perplexity goes from 78.3 to 88.5. And because for perplexity, lower value is better, 88.5 is quite worse off than 78.3. And the story remains the same when you're talking about LMF. So none of these traditional compression technologies are good enough for us to compress networks by these large factors. So that's when sort of motivated us to look beyond them and see what we can find. And that's when we ran into Kronecker Products. So before I get in,
can I ask a quick question? Some burning questions from our audience. What is the LMF you referred to in the previous slide?
So yeah, LMF is a low rank matrix factorization or any versions of it. So you take a larger matrix, express it as a product of two smaller matrices. So that you do that in say something like an SVD sort of scenario, or you can do it in corporate during training also. Okay, so to move forward, so before I get into why Kronecker Products, I'll explain a bit about what are Kronecker Products. So the Kronecker product is a block-based matrix multiplication algorithm. So the Kronecker product of two smaller matrices A and B gives you a larger matrix C. If A is of size M cross N and B is of size P cross Q, you get an A cron B of size MP cross NQ. And the way it does that is that it takes each element from the matrix A, scales the matrix B, and sticks it into the different quadrants of the larger matrix. Now, if this seems a little complicated, let's just walk through a very simple example, and hopefully that might make things simpler. So again, you're talking about C matrix expressed using Kronecker product of two smaller matrices A and B. Now, Kronecker products of if A is of M cross N size, B is of P cross Q size, then A cron B is of size NP cross NQ. So C would be of size 4 cross 4. Now you take 1 from A, multiply or scale the matrix B and stick it in the top left corner. Similarly, you do that. You take 2 from A, scale the matrix B, stick it in the top right corner, and then you get bottom left and bottom right corner. So basically, you have taken the elements of A and B to create the larger matrix C. Ideally, C would have required 16 parameters because it is 4 cross 4 size, but because C is created from A and B, you now only require 8 parameters. So the way C is created, sort of to remember the fact is that the elements in A and B influence multiple locations in C. So one here influences 4 locations and similarly other values. So now we saw 2x compression, but the power of Kronecker products lies in the fact that as the matrices get bigger and bigger, the amount of compression also gets larger. And as you know, in a neural network, all of the weights values are basically matrices, be that CNNs or LSTMs. So in this case, if C is of size 256 cross 256, that is your matrix or LSTM layer is of size 256 cross 256, and you express as a Kronecker product of two smaller matrices, A and B, then A and B will be of size 16 cross 16 each, and that will give you 128x compression when you represent the large matrix using Kronecker product of two smaller matrices. Now, large compression alone does not guarantee the usefulness of a compression tool. You really have to preserve accuracy also at large compression factors. And that's where Kronecker Products starts getting very interesting. Now, Kronecker Products preserve rank of a matrix at large accuracy. So for people who are not familiar with what a rank of a matrix is, the rank of a matrix is the notion of capturing the expressibility of a matrix in a neural network. So the more the rank of a matrix, the more expressible that weight matrix is in your neural network. And if the weight matrix is more expressible, what that means is that you might end up with a higher accuracy for an application during training. So here again, we look at the C matrix of size 256 cross 256. Now, before compression by Kronecker Products, the rank of C was 256. That is, the matrix C has you can imagine as having 256 different degrees of freedom. After 128x compression, that is after you express C as a Kronecker product of two smaller matrices A and B, the rank of C still remains 256. That is, even after 128x compression, the expressibility of the matrix does not change. Now, even if a particular compression technology is able to preserve accuracy, it might still not be useful because either you require a fancy hardware to sort of implement or run that compression technology, or the existing libraries might not support it. So that's where Kronecker products become even more interesting. Kronecker products can run on existing hardware because during inference, what you end up requiring is just matrix multiplication algorithms. So again, matrix multiplication algorithms are workhorse of a neural network. That's the compute that you run during inference on a neural network. And in Kronecker product, the matrix vector multiplication translates into two small matrix multiplication algorithms. So the ops reduction that you see after compression also translates into real-time inference benefit. And we'll see that later on. So there are a lot of other things that I have sort of skipped, but I do encourage you to read this paper that you have written, which talks about the methodology a bit more. But what I'll do is walk through some of the results and sort of hopefully that motivates you a bit more to go back to these papers. So the way we train a neural network using Kronecker products is that we take all of the weight matrices in a neural network and replace them with Kronecker products of two smaller matrices and train them from scratch. So Kronecker products is included during your training phase. So we look at 4 different applications: keyword spotting, human activity recognition, and a couple of image recognition benchmarks. We compress them using 4 different compression techniques: low rank matrix factorization or SVD, pruning. Small baseline is basically take a neural network and manually make it smaller by reducing the number of layers or reducing the size of the neural network, and then Kronecker products or KP. And after compression, we actually measured the inference. We implemented these compressed networks using Eigen library and measured inference runtime on a Hikey 960 board. And the results were really compelling. So if you look at the KWS or keyword spotting application, when we compress them by 20x, what we see is that traditional compression technologies can lose 3 to almost 8% log accuracy. But with Kronecker product, you end up only losing 1.2% accuracy. And the runtime is also reducing from 26.8 milliseconds to 17.5 milliseconds. With HAR or human activity recognition, after 30x compression, you preserve most of the accuracy. You only lose 0.7% accuracy when you go from baseline here to the KP compressed network. And none of the other traditional compression technologies are closer to what KP can provide you. And the runtime again goes back down from 470 milliseconds to 157 milliseconds. And again, the story remains the same if you look at these small image recognition benchmarks that we run. But for the purpose of brevity, I won't go into a lot more details. So hopefully by now, at least you are convinced that for the IoT workloads, at least the ones that we have seen in this presentation, KP compression does really work well. If there are more questions, I guess this would be a good time to take those questions away.
Sure, let's address some questions from our audience. So I think one of the questions from one of our audience here is from energy consumption perspective, is the compression method uses more energy on the device than without using compression for the similar applications?
All right, so that's a good question. So the way I see it is that, so this is not an on-the-fly compression, right? So you are deploying the compressed model in itself. Now, KP gives you 2 advantages. It reduces the size of your neural network and also the op count. So for me, the energy consumption is a function of how many values that you're going to read from your SRAM or your flash memory, and how many times your Mac units are going to be executed. So because you are reducing the size of the network significantly, that means your number of things that you read from your flash memory or SRAM are quite small. And because your ops are also reduced by a large factor, so the number of times your Mac units are used are also reduced. So given that you are seeing a reduction in everything that actually consumes energy on a device, we should see an energy reduction, but we don't have those numbers.
Okay, next question. Does Kronecker Products have advantages over FFT or JPEG compression, where the accuracy of loss in DCT can be controlled by the amount of AC frequency trained?
So I am personally not aware of JPEG compression being used to compress neural network workloads, and that might just be a limitation of my knowledge. So even with Kronecker product, you can actually control the amount of compression that you get. It's not that you don't have a knob to control the amount of compression. So you have this accuracy compression trade-off that you do. Again, I skipped those details from a parity point of view, but if you read the paper, that will be available.
Thank you. So next question, I would expect the runtime to increase slightly, typically of compression, decompression pipelines. Could you give an intuition of why the runtime also decreases?
Right. So again, with Kronecker product, you really don't have to decompress to get the larger matrix. When I say that op reduction that you saw previously, uh, I skipped the linear algebra trick. So basically, you now work on compressed data. That is why here you saw that for a matrix vector product, in an ideal scenario, you would have expanded this A cron B matrix into a larger matrix C and then did CX. But linear algebra allows us to directly operate on the compressed matrix. So because there is no decompression phase and you're directly operating on a compressed network, you see your ops reduction actually translates into speed up or actual inference time speed up. And that is why you see the numbers going down from 470 milliseconds to 157 milliseconds.
Thanks. Can you comment on the similarities or differences between your work and product quantization that uses k-means to compress the weights?
Right. So from what I understand, again, my understanding of product quantization is quite limited, but for k-means, you need a trained network and you sort of start from a trained network to find weight clusters that enable that. So, or you might actually do a k-means aware, you can actually do a k-means aware training. So I would think that Kronecker products has certain similarities to it, but the different properties of Kronecker products when it comes to the inference runtime benefit because you're not calling you're doing a simple two matrix multiplication calls during inference instead of lookup that you might do in a k-means clustering algorithm. And the fact that you preserve all of the rank of a matrix after um, compression makes it different from something like product quantization, where you are, at least in my view, in product quantization, what you're learning is a low dimensional basis which combine to give you the larger matrix. But that comparison I haven't made, but that's my intuition as to why KP would be better.
Okay, one more question for now. Are these networks trained from scratch?
Yes, these networks are trained from scratch. So what you do is that you get the backbone architecture that you want, and in that backbone architecture, all of the weight matrices are replaced as Kronecker product of two smaller matrices, and then you train them from scratch. So you don't really need a trained network to start with. All you need is a backbone architecture.
Thank you. Yeah, do you want to finish the rest of your presentation? And
Sure,
we can
okay.
revisit these open questions.
All right, okay, thank you. So yeah, at this point, we sort of realized that Kronecker products works for the IoT workloads, at least the ones that we had or we were running within our lab. Now we wanted to see if we can actually use Kronecker products to compress larger workloads. So with Kronecker products, the amount of compression gets bigger and bigger as the matrix gets larger. So we were really curious about especially compressing large NLP application, or at least I was, because to me, chatbots are going to get really interesting in the future, and they're going to be driving a lot. They have the potential to drive a lot of hardware and how they behave or sort of are made in the future. And chatbots need to be an always on application, or can be an always-on application, so running them on a smaller device with longer battery life would make sense. However, chatbot applications are also large, right? So we thought maybe we should try KP to compress this large NLP application. Now, the KP did give you an insane amount of application, but the accuracy loss was just unacceptable. So if you are losing 27% of your baseline accuracy, you have basically rendered that particular application useless. So then that sort of raised the questions. KP worked for IoT workloads, but it did not work for large NLP applications. So what happened? What broke in a larger application? And then the question becomes, how do we solve it? How do we still maintain the goodness of KP and sort of promote its adoption in NLP workloads also? So to understand what broke, we need to again take a step back and see how KP generally operates, right? So KP, so this is a slide that we looked at earlier. So KP of two smaller matrices gives you a larger matrix C. And the way that happens is that you take each element from A, scale the matrix B, and stick into the different corners of the larger matrix. So that way, using few parameters, you create a larger matrix, right? And if you look at it, each parameter in the smaller matrices ends up influencing large number of parameters in the larger matrix. So here one influences 4 parameters, 2 influences 4 parameters, and you can go on and on. So the matrix C has a fixed structure. So the matrix C doesn't really have all that additional degrees of freedom that it wants, right? If you want to change something in the matrix C, you need to go back in the smaller matrices A and B to change that. And that has an issue. Now, suppose during your neural network training, during backpropagation, you figure out that, say, backpropagation figures out magically that this value needs to change from 2 to 4 to get to that right minima that gives you a really good accuracy. In an ideal neural network, changing this value from 2 to 4 is easy. All parameters do not have a fixed structure, they operate independently. But in a KP with a fixed structure, the independent operation does not exist. So if you want to change this value from 2 to 4, you might be able to change this value from 2 to 4 because this value 2, if you remember correctly, was created by multiplying this 2 with this one value in P. But if you change this value from 2 to 4, all these 4 values also change because all these 4 values are created by multiplying T2 with the smaller matrix B and sticking that product into, or the product into the top right corner. The next way you can do it is you change this value from 1 to 2, and that should change this value from 2 to 4 because you are creating this by multiplying 1 into 2. And when you do that, however, all the other 4 values change. So what is happening? Your minima, to get to your minima for good accuracy, you wanted to change one value, but you end up changing more than one value. So in a way, if you can imagine, you keep dancing around the minima, never getting to the point you want. And this behavior is actually exaggerated in a larger network because in a larger network, the smaller matrices have a bigger influence. That is, each value in the smaller matrix ends up influencing more values in the larger matrix. And that is the reason why we get the larger compression factor with larger matrix, but that also means that the structure becomes more and more rigid when the matrices become larger and larger. So then the question becomes, we understand now why this is happening, but the question becomes, how do we fix this? So the problem was the fixed structure of Kronecker product. The fixed structure of Kronecker product did not allow us to give the additional degrees of freedom that some parameters might require. So the way we give that additional degree of freedom is to simply add a very sparse matrix on top of the Kronecker product matrix. So we wanted this value in the Kronecker product matrix to have the additional degrees of freedom, which we are not able to provide because of the fixed structure. And the way we do it is that we add a sparse matrix where the non-zero value in that sparse matrix corresponds to the location in the Kronecker product matrix that needs the additional degrees of freedom. And then basically your weight matrices in neural network are replaced by a sum of two matrices, the Kronecker product matrix and a very sparse matrix. And this resultant compression technology, or a tool that we have sort of discovered, we are calling it doped Kronecker product. Now, doped Kronecker product still leads to compression because your large matrix has been replaced by a Kronecker product matrix, which gives you a large amount of compression. If you remember, for the 256 cross 256 size matrix, you are getting 128x compression, and for larger and larger matrix, the compression factor increases. And so that matrix is in a very compressed format, and the other matrix is a sparse matrix, which after CSR representation is also in a very compressed format. So overall, you still get a large compression factor using doped Kronecker product. So the way you use a doped Kronecker product is that you take the weight matrices in your neural network replace them as a sum of two weight matrices. So all your weight matrices in a neural network are replaced as sum of a Kronecker product matrix and a sparse matrix. The sparse matrix is initially dense, it's completely dense, that is, there is no compression there, but over time you significantly prune it, and the pruning amount of sparse matrix determines the amount of compression. And the hope is that, or what happens is that backpropagation realizes that certain elements in the Kronecker product matrix need that additional degrees of freedom, and the way and those locations are in a non-zero value in the sparse matrix. So for people who are from a classical machine learning background, this is basically an inspired technique from robust PCA. So again, there are a lot more details that I'm skipping right now. I'll really encourage you to go read the paper if you find this interesting. What I'll do is actually talk about some of the results, and hopefully they might convince you to at least go and then look at that paper and then see if that might work for you. So again, here you are looking at the same chatbot application that we saw earlier. And then for that chatbot application, as I said, what you're measuring is the perplexity score, which is the accuracy metric. And for perplexity score, the lower value is better. So when you're comparing perplexity score and compression factor on a graph, things that exist in the bottom right corner are the best, because the bottom right corner gives you the locations which give you maximum compression and preserving most of the accuracy. So what you see here is interesting. At around 20x compression, pruning and DKP are the only compression techniques that are competitive enough. Every other traditional compression technologies, this is low rank matrix factorization, the training aware low rank matrix factorization, or SVD, and this is small baseline, which means you have scaled down the neural network to get to that compression factor. And what you see here are different papers that have sort of compressed the same application. And none of these compression technologies come close to DKP and pruning at 20x. And in fact, at 25x, DKP outperforms pruning by almost 8 to 9 perplex, or maybe 6 to 7 perplexity points. So DKP is able to preserve almost all of the baseline accuracy at around 25x compression. So this is sort of the end of my presentation. Hopefully you would have learned something new. Hopefully you understand the two new compression tools that we are exploring, KP and DKP, and then you're excited about it as much as I am. And then hopefully you're convinced that these compression technologies can give you large compression factors, better compression results than traditional compression technologies like tuning or low rank matrix factorization. We have shown you that the KP and DKP can actually run on existing hardware using standard neural network libraries, so you don't really need to invent something else. And if you go read the paper, you'll see that at least KP compressed networks can be further combined with quantization. That is, 8-bit quantization works with KP compressed networks. We still have to run those experiments for DKP, but at least quantization works for KP compressed networks. So this is the end of my presentation, so I'll be open to more questions if they are available.
Thank you. Let's try to address a couple more questions here. So first question, is there an open tool which our audience can access to compress their own models using the techniques you just introduced?
Right, so the short answer is no. This is still something that is in the research phase. For a slightly longer answer, the papers that I've pointed to, if you look at the appendix sections, I give you the algorithms and the pseudocodes that you can use to implement these compression technologies within TensorFlow. So TensorFlow, because KP, as I said, turns into two matrix multiplication library calls during both inference and training, implementing it within TensorFlow is quite easy. And I have provided the required code in the paper appendix section of the paper that you can go and use and sort of to train your algorithms. Then the point comes back to the deployment point of view. So from a deployment point of view, again, the libraries exist. What doesn't currently exist is the API. And then that's mostly because it's only been fairly new. This compression technology or tools that we have explored, it's only been the last 6-7 months of work that I'm talking about. So pushing them to, say, a TensorFlow Lite would require a bit more work. Things like pruning and low rank matrix factorization, they have a wider adoptability and have existed for almost decades. So they might exist as an API form from a deployment point of view. KP is slightly new. It's slightly niche. So it would, I would imagine it would take a bit more work in terms of even more applications. So we already done it on 7 to 8 applications. but we need to scale up the number of applications to convince the ecosystem to include an API for that. But yeah, from a technology point of view, because of the simplicity of this method and the fact that all you require is 2 matrix multiplication call, once that decided, adopting it should be easy.
Thank you. We only have time for one more question. We have more than one attendees asking, is the technique you introduced that can be applied to CNN models? There seems to be something more general than RNN.
Yes, and that's a great question. So that's a question that we also have. We haven't really answered that question. And the reason for me to choose LSTMs over CNNs was that, at least for CNNs, I saw a lot of work from a NAS point of view, channel pruning, magnitude pruning, and random pruning, and even sub 8-bit quantization that I thought, okay, let me first start with LSTMs. But now that it works for LSTMs, we are going to explore, or we are planning to explore it for CNNs. And then we are planning, once we do that exploration, we are planning to make more comparative comparisons with all the other techniques that are used for CNNs.
Thank you, Urmish, for your great presentation. We still have a lot of questions we're not able to address during this live session. We will answer them on our forum. So on your screen, you see a pop-up dialog collecting your feedback about our tinyML talks. Please take a moment to finish it. We value your inputs. Big thank you goes to our tinyML talk sponsors, DeepLight, Kixel, Edge Impulse, Reality AI, Maximum Integrated, and ThinkSense. Again, if you are interested in sponsoring our program, please email betty@tinyml.org. So DeepLight provides an AI-driven optimizer to make a deep neural network faster, smaller, and energy efficient. Edge Impulse offers online tinyML lifecycle solutions, which transform developers' abilities to deploy machine learning to embedded devices. Maximum Integrated enable edge intelligence with their sensors and signal conditioning technologies. Advanced AI acceleration solution is coming soon. Kixel's AutoML platform builds tinyML solution for the edge using different sensor data. Reality AI offers optimized feature discovering, compact embedded code, and optimization toolkit. They also provide tools for managing the cost of data collection. ThinkSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Again, please join us on September 1st, Tuesday at 8 a.m. Pacific time to learn from our speakers from Arizona State University and BrainChip. If you have other proposals for our tinyML talk sessions, please email your proposals to talks@tinyml.org. Thank you for your participation.